Today I want to talk about information cascades. This is stuff that happens all the time. People copy other people, and sometimes people start doing stupid things because one person does something, the second person copies, and so on, and then they're all doing the same thing. Okay, first 2 seconds of respect still for the Ukrainians who are fighting for their freedom, for ours. Now I want to show the last, so now we have 3 lectures left, and I want to talk about cascades. Cascades is how information moves around because of the network. And there's 3 kinds of cascades that I want to talk about: information cascades, direct benefit cascades, and network structure cascades. So the information cascades is something very simple. It's when you have decisions made in order, 1, 2, 3. If I decide to buy a certain car, friend sees me, buys the same car, the third person will look at us and say, maybe I should buy the same car, and everybody does the same. It's called sequential decision making. And we're going to do a lot of probability. So I'm going to show you Bayes' rule. So probably you've seen already Bayes' rule, right? You understand very well Bayes' rule? Yes? Great. Well, we're going to use it, but I will explain it. And then next week and the final week, we're going to talk about different cascades. The second one is direct benefit. It means I get a benefit when using Microsoft Word because everybody uses Word. That's kind of called the net benefit cascade or network effect. And the final one is network structure. Depends on who I know. So information propagates from one person to the next, and maybe it stops somewhere. So that's the third one. So different ways how information can move around in the network. Okay. So today I'm going to tell a lot of stories, and it's going to be lots of bits and pieces. So I'll try to make it very, very clear. So I'm going to start with some stories. The idea is people in the network are going to influence each other, and sometimes it has a big effect. So here's an example of an information cascade. Choosing a restaurant, A or B. I either go to Mexican restaurant or Indian restaurant. It's 2 restaurants. And I have chosen restaurant A. I looked on the internet, figured it out, and I go to restaurant A and I see it's empty. Nobody there. And there's restaurant B right next to it, which is full of people. So what do? So maybe it's a good idea to join the crowd at B. Maybe. Because maybe the people at B have independently figured out that that's the better restaurant. And maybe they did work that's better than your own research. So maybe you should go to B. Or maybe that's a mistake. We'll see. But let's say you assume that the people at B have decided, have information, and they decided that B is better, so you choose B. And this is called herding. People act like a herd of cows or of some animal, lemmings. One of them jumps off the cliff, and they all follow, okay? This is called an information cascade, when people are doing what the other people do. That's what we're going to look at today, how it works. Okay? So, what is an information cascade? So, people are making decisions. I want to go to A or B. Someone else is making a decision. And the idea is that later people will watch the earlier people. I will see what other people did before me. And maybe I follow them. So a cascade occurs when I abandon my information in favor of the other people's information. So inference. So I don't really know everything. I make some inference, and I assume other people have reasons to do it. So it's rational. I think the other people have good information, so it's not just mindless. People are trying to be rational, and this kind of cascade happens when people are rational. They try to take into account information. So you want to figure out what to do from limited information. You see a few people deciding, and you decide. So it's not the same as social pressure. Huh? Social pressure is different. Social pressure is you don't think. There's no rational. You see everyone doing what you do without thinking. Here you're actually thinking. Okay? And there's two main kinds of cascades. Information cascade or direct benefit cascade. In information cascade, it's you are making inference. You're trying to be rational, and you're figuring out that this is the best decision for me. That's what we're talking about today. But in direct benefit cascade, that's what we'll talk about next week. This is that you actually have a benefit. Fax machines. So I mentioned Microsoft Word or something. If you do something that a lot of people are doing, you get a benefit because there's a lot of people. Okay, so I'm not going to talk about that today. Today it's going to be reasoning, rational inference. Okay? And I'm going to make some scenarios for that. And then we're going to do reasoning on probabilities, and we're going to use Bayes' rule. So I'm going to talk a lot about Bayes' rule today, and hopefully it will help you understand better Bayes' rule. You've all seen Bayes' rule, so you understand very well Bayes' rule or not? You remember it? Conditional probabilities, we'll see it. Okay. And we will define an idealized model. So we're going to do some mathematics with probability. So I'm going to start by doing a simple experiment, and we make like a scenario. And then I'll talk about Bayes' rule, because we have to do reasoning. So we're going to compute probabilities. And then we have our idealized model. It's sequential decision making. People make decision on what they know, private information, but also what they see, the other people, the earlier people. So I have some information, secret information, but I also see what the other people did. And then I make a decision. Okay? And then we're going to conclude how it works. I'm going to start by a simple kind of experiment. So this will hopefully give you a lot of intuition of what's going on. Okay, so the simple experiment, and then the mathematical model is going to be closely connected to this. Okay, so how does it work? You have to make a decision. Do I buy iPhone or Android phone? Or do I wear a different kind of shirt or whatever? And the decision is made sequentially. It's not all at the same time. So I make a decision, and I can see what people before me they did. Okay, so it's sequential. That's important. And I have some private information. So I know something, but I also see what the other people do. So there's two kinds of information. There's what I know, my secret information, my local, my stuff, but also I see the other people's decision. So that's what I know, and for that I try to make a decision. So here's the experiment. So we have a classroom. Like here with students, we have an urn. An urn is a pot like this, and there's 3 marbles in there, and 3 marbles, and there's 2 possibilities. Either 2 of them are red and 1 of them is blue, or 2 of them are blue and 1 of them is red. Okay, so it's either majority red or majority blue, but I don't know which. So that nobody can see inside. Okay, so there's 3 marbles, and it's either majority red or majority blue. So a student comes to the front, sticks his hand in the urn, picks out a marble, looks at it privately, puts it back, and then makes a guess. Is it majority red or majority blue? Okay? So the student doesn't look at everything. The student only sees one marble and looks at it, and it's private. Nobody else sees. And then the student makes a public decision. I guess it's majority red, for example, or majority blue. And then the second student comes and does the same thing. Okay, so there's an order, 1, 2, 3. And each student can see what the previous students did. Okay, you see how it works? So here's some results. So it's for the student, the first student. What does the first student do? Well, I pick a marble, and if it's red, I guess it's going to be majority red, okay? Because it's more chance, 2/3. So if I pick a red one, then there's more chance that it'll be majority red than majority blue, so I guess majority red. But if I pick blue, I guess majority blue. Okay? And interesting, important, the guess gives perfect information about what I see. That means I announce to everybody, I say majority blue. That means everybody knows I saw blue marble. Okay? So because of my public guess, they know I saw blue marble. Okay? Now the second student comes. It starts getting more and more interesting. Picks a marble. And there's two possibilities. Maybe it's the same color as the first, or maybe it's the opposite color. So if the second student picks blue, and the first one also picked blue, then the second student will also say blue. But if the second student picks a red, then I know there's one blue and one red. The second student knows the information from the first, that there's one blue, and he knows also his own information, which is one red. So he knows there's one blue and one red. So what does he guess? So it's a tie. Red and blue are the same. So he breaks the tie by guessing the color he saw. So that gives the most information. So if I pick a red, I will say red. That means the first student said blue, and the second student says red. Again, I have all the people in the audience have perfect information. They know exactly what I saw. If I say red, they know I saw red. If I say blue, they know I saw blue. So for now, whatever I say gives perfect information about what I know. Okay? And now the third student comes along. Okay. Now what happens? Well, there's two possibilities. If the first two were guessing opposite, blue-red, the third guesses what he sees. Okay? So if it's blue-red and the third one picks red, then the third one will guess red. Because there's two reds and one blue. Okay? But if the first two guessed the same, so if they guessed opposite, then the third one guesses what he sees. If the two guessed the same, if the first and the second both said blue, then whatever the third one picks, blue is already majority. I mean, there's two blues and one red. So if they guess the same, and if I pick a red, that means I know that there's been 3 trials, 2 blues and 1 red. So blue is still the majority of what people picked. So there's the biggest chance, rational, the biggest chance that it's blue. So if the twos guess the same, then I will always say the same thing. Doesn't matter what I pick. Okay? So if the two said blue and I pick red, I will still say blue. If I pick blue, I will also say blue. I also always say blue. And the other students in the room, they don't see that marble, what I saw. They don't see it anymore. They know nothing about it. Now I I'm just repeating basically what the previous ones did. This is information cascade. Okay? Starting now, everyone is going to keep saying blue. And nobody's going to say anything else. And it's rational. Okay? So that's an information cascade. It happens if the first two guess the same. And the fourth student, so now the fourth one comes. Now assume that the information cascade is started. So the first two saw blue, the third one says blue, and the fourth one. Well, the fourth one, no matter what marble they pick, they know there's been two blues. So they will all, and that the third one has no information, they know that. So they will also say blue. So rationally, the fourth one will say blue, and the fifth one will say blue. Everybody will say blue after that. Okay? That's a cascade. The cascade goes on. Notice the cascade can be delayed. So let me make a diagram here. This is the students. Let's say the first one sees blue, the second one sees red. Okay? Now the third one, if the third one sees red, he will say red. If the third one sees blue, he will say blue. Because if he sees red privately, then there's two reds out of three. If he sees blue here, then there's two blues. Okay? Okay, good. And now the fourth one sees red or sees blue. Well, it doesn't matter somehow. Well, no, if the fourth one sees red, then this one says red, red, he will say red. Okay? If the fourth one sees blue, then that makes blue, red, red, blue. That makes a tie, and he does a tie break, says blue. Okay? Now, here we have blue, red, red, blue. So there's a tie, so there's no cascade yet. But here, it's red, 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 blue. It's going to be, everyone is going to say red. It's going to always say red. This one is a cascade. So if there's two reds, if the reds get a majority, then it will be a cascade. If it stays evenly matched, the cascade is delayed. Okay? So you see, sometimes the cascade happens, and sometimes doesn't happen. Okay? So you see kind of what's going on, huh? And each student is being perfectly rational. Is saying the number, is saying the color that gives the highest probability. Okay? Okay, so what can we conclude from this little experiment? First of all, first conclusion, it's very easy for a cascade to happen. Huh? You can say right here, it's happening immediately, very quickly. It's very easy. It can even happen after two students if they both see the same thing. Huh? So it's very easy for a cascade to happen. Even if the students are being completely rational, the choice can be locked in. Okay? So it's not social pressure, huh? They're being rational. Second conclusion, well, it's not always optimal. If this one says red, we have red cascade, well, maybe the urn is majority blue. Maybe it's a mistake. The majority is what they say is not always what the majority is in the urn. Huh? So if you have a majority red urn, so two reds and one blue, there is 1/3 times 1/3 chance that the first two students will see blue, 1/3, 1/3. That means 1 out of 9 chance, and of the whole thing being a mistake. So a cascade can be wrong, okay? It can be totally wrong, and actually that happens a lot. It's by far not optimal. Okay? Third conclusion, it's fragile. I mean, it's very easy to make a cascade, but you can also break a cascade. So let's say there's a long run of blues, but students 50 and 51, so very long. They both draw red, and they cheat. And they show, look, I have a red, haha. Well, the cascade of blue is broken. And now they're going to start saying red, okay? So if you stop following the rules a little bit, it's very easy to break a cascade. Student 52, even now he's completely rational. He knows that there's 4 pieces of information. Students 1 and 2, the ones who started the cascade, but he also saw the marbles of 50 and 51, so he has 4 genuine pieces of information. 2 blues and 2 reds. 2 red and 2 blue. So student 52 is now a tiebreaker and doesn't have to say red anymore or blue. So the initial run, the first 49 blues, it's very light. There's no information in there, almost. There's only 2 pieces of genuine information in there. Students 1 and 2. All the others are basically just repeating, okay? But even they think they're being rational. Each one is maximizing the probability. Okay? So that gives you some intuition. And this happens a lot, actually. And I'll explain later what happens. In Belgium, there's certain things that are favoring cascades. Okay? So it actually happens a lot. Okay, so that's kind of the intuition. Gives you some intuition on cascades. Now I want to make a little detour, and I want to talk about Bayesian. So we're going to do a lot of calculating with probabilities, and I want to give you good intuition on Bayes' rule. So this is kind of refresher, but if I guess well, then maybe it's a good idea to refresh. I think this will help you better understand Bayes' rule. Okay? So I'm going to make a little detour. I'm going to make a discussion of Bayes' rule. We're going to apply Bayes' rule, and then we'll apply it to the hurdle. We'll see. Okay. What is the probability of something given that I know y and the previous person asserted z? So what is the probability of majority blue given that I have a red marble in my hand and that the previous person said it blue? So it's conditional probability. I have partial information. You have to reason when you know bits and pieces, okay? You have partial information. In order to do that, you have to use conditional probabilities and Bayes' rule. So that's what we're going to explain. So, okay, so I'll first define what it means. We're going to talk about probabilities. So we have an experiment. We do something. There's some possible outcomes. I roll the dice. It's 1, 2, 3, up to 6. And so all possible outcomes is 1, 2, 3, up to 6. An event is a set of possible outcomes. For example, that the dice the number is even, 2, 4, 6. So an event, A, is a subset of all the possible outcomes, and it has a probability of A. And we will assume that every event has the same probability. That's something usually you have to verify. Then the fraction of outcomes in which the event occurs gives us the probability. Okay, that's very straightforward, and we can assume usually it's K. If we think, good, well, if you roll dice, each number has the same probability. Okay? So here's our sample space, the rectangle. We have two events, A, which is a subset, and B, which is a subset. There's also a joint event, A intersect B. This is where both events occur at the same time. So that's the overlap, okay? And we want to do conditional probability. The probability of A given that B has occurred. So this is called conditional probability, and it's denoted by the probability of A given that B occurred. Okay? So that's what we want to compute. Let me make some board. So it's very simple, but you have to be careful because it's very easy to get confused with Bayes rule. Okay? So the probability of A given that B occurred, we can define it from here. So if B occurs, that means we're inside the B ellipse. And we're interested in A, so A intersect B. It's the fraction of events inside B that are A intersect B, okay? So it's the probability of A intersect B divided by the probability of B. And we can also, likewise, give the probability of B given that A has occurred. And that's the probability, again, of the intersection, B intersect A, divided by A. So we assume A, and we're inside of A, so there's B intersect A. Now, what's really important is that these two numbers, we can connect them. And this is what Bayes' rule tells us. We can say that probability of A intersect B, you can do the computation, is equal to probability of A given B times the probability of B. And you can do the same for the other one, which is the probability of B times the probability of A. And then if you simplify, you could get the relationship of probability of A given B. And so this is called posterior probability. So we have stuff happening, and B happens. B happens, and that changes the probability of A. So the prior probability is when we don't know if B happens. So that's probability of A. But once B happens, you get what's called the posterior probability. So the probability of A will change. Okay? It's A given B, and it's probability of A times, and here we have a kind of correction factor. Okay? So this is Bayes' rule, which I will write here because we're going to use it. So the probability of A given B is the same as probability is equal to probability of A times the probability of B given A divided by the probability of B. Okay? So this is how we connect them. This one is called the prior probability. This one is called the posterior probability, the one after. Okay? So this is before B, this one is after B, and this is a correction factor. So the probability of A will change. When new information comes in, then probabilities change. So we know that A has 50% chance, but then B comes in, and the probability of A will change. Okay? And it can go up or down. It doesn't increase or decrease. It can either go higher or lower. This number can be bigger than 1 or less than 1. Okay? This correction factor. So this is the probability of B given A divided by the probability of B. So it's somehow the effect of A on B here, in this correction factor. Okay? So this formula is called Bayes' rule. Seems very simple, but we're going to make some examples of it. Okay? so that you can understand really what's going on. We can apply Bayes' rule to compute probability of something given that we have some other information. Okay? So if we have some private information, changes the probability of the event, or we observe some other stuff, it changes. So here's an example. And this is a typical kind of application of Bayes' rule. This is eyewitness testimony. So this example is like, lawyer in a law court. Okay, so in a particular city, 80% of the taxi cabs are black and 20% are yellow cabs. Okay? A witness, so there was a witness, there was an accident, hit and run. So a car hits another one and drives away. Says there was a taxi involved and it was yellow. It was a yellow taxi who did it. But that's not always 100%. So witnesses, because it goes so fast, sometimes they misidentify. So if it's really yellow, they will say yellow 80% of the time. If it's black, they will say black 80% of the time. But 20% of the time they make a mistake. Okay? They don't misidentify. So the question, what is the probability that the cab is yellow if the witness says it was yellow? It's not 100%, this is a conditional probability, and we can use Bayes' rule to figure it out. So we're looking for the probability. So here the true color, true is yellow, given that the witness report is yellow. Probability that the true color is yellow if the reported color is yellow. So what is that? Well, we know some things. There are some things we know and some things we don't know. We know that the witnesses make mistakes. We know that 80% of the cabs are black and 20% are yellow. So how do we figure this out? It turns out with Bayes' rule, we can figure this out. Okay? So here's the computation. We want to figure out the probability that the true color is yellow if the reported was yellow. So this is equal to the true probability that's true times this correction factor. So the probability that true is yellow, given that your witness report is yellow, is the probability that it's yellow by itself, with no condition. So this is the fraction of cabs that are yellow. Okay, so this is 0 point. So the fraction of cabs that are yellow, 20%, times this correction factor. So we have the probability that the report is yellow if it really was yellow. That's the probability that the witness made a truthful report. So the witness, if it's yellow, they will say yellow 80% of the time. Okay? That means the probability that they say yellow, if it was yellow, is 80%. Okay? And now, what is the probability that they will say yellow? Well, this one is a little bit harder to compute. Because we know they will make mistakes 80%, say the true thing 80% of the time, make mistakes 20% of the time. Okay? So the probability that they will say yellow is the probability that they don't make a mistake and the probability that they make a mistake. Okay? So the probability so there's two cases here. So the true taxi cab color is either yellow or black. And these are independent events, yellow and black. Yeah, taxi cannot be both yellow. So the probability that the report is yellow is the probability when it's true and the sum when it's black. Okay? So we have two cases. And we can add them up because they're independent. Okay? It's one or the other. So the probability the true color is yellow, and then that the witness reports yellow, given that the true color is yellow, plus the probability that the true color is black, and the witness reports yellow, even though the true color is black. So this is 0.2 times 0.8 plus 0.8 here, 80% black times 0.2. That's 0.32. Okay? So the probability that the witness will say yellow is 0.32. They will say yellow no matter what. Okay? So this is our computation. If you compute this, you can actually compute this. So 8 times 2, this is 0.16. Divided by 32, this is 50%. So if the witness says that the cab is yellow, then there's a 50% chance it really is yellow. Not 100%. It's only 50%. But that's actually pretty good, because there's only 20% cabs in the city. So the witness report has increased the probability yellow, that the cab is yellow by a lot. Okay? So the 20% has increased, becomes 50%. So this increases our belief that the cab is yellow. But it's not 100%. Huh? You can see that you have to be careful, because the witnesses can make mistakes. So that's what we compute here. Right? So Bayes' rule lets you compute the posterior probability from the stuff we know. Okay? See how it works? Bayes' rule, you're getting Bayes' rule, good. I have another example which is more interesting, maybe. Spam detection, email. So spam filters will often use Bayes' rule. Okay? And how does it work? Well, suppose you receive a piece of mail and it says, check this out. What is the chance that it's a spam? Okay, so this is a conditional probability. The probability that the message is spam, given that the subject says, check this out. So I'll just write it like this. Probability that it's spam, given that it says, check this out. So we can compute this, again, this probability. This is a posterior probability. We have a prior probability. Assume that in general, you get 40% spam. So probability of spam is 40%. That's in general. But now we want to have better information about this particular email. This is just general number, assuming it's for all messages. And we also know this. If the message is spam, 1% of the spam says, check this out. But only 0.4% of non-spam says, check this out. So the probability that there's a check this out if it's spam is 1%. The probability that there's a check this out non-spam is 0.4%. So the check this out is different for spam and non-spam. Okay? So now we can use, again, Bayes' rule. Like in the previous experiment, so the probability that it's spam, given that it's check this out. So instead, again, we start with the prior probability, 0.4, and we want to know what is the posterior probability. Does it get higher or lower? And then we multiply it by this correction factor. So the check this out when we have spam, and divided by the check this out in general. So the check this out when we have spam is, we know it here, it's 1%. But to check this out in general, we have to see whether it increases or decreases. Okay? So to check this out in general, again, there's two possibilities. Either the message is spam, or it's non-spam. And those are exclusive. So we can add up the two cases. So probability of spam times, check this out, if it's spam, or plus the probability of non-spam with check this out if it's non-spam. And if you can figure these two out, this is 0.4, non-spam is 0.6, multiplied by 1% and 0.4%. Okay? And if you do the computation, you get 0.4 times 0.01 divided by this. So it's like this, it's 0.4 times 0.01, 0.0064, like that. So this is already really simplified. This, and you get 0.625. That means the posterior probability is higher. It went up. It goes from 0.4 to 0.625. The prior posterior. So to check this out, when we receive it, it increases the probability, the likelihood that the message is spam. It goes from 0.4 to 0.625. So it's, in the spam filter terminology, it's a signal. It's a signal saying, hey, maybe it increases the likelihood. So it's like a trigger signal for spam. And the more signals you have, the higher and higher the probability gets. So in a realistic spam filter, you'll have lots of signals. Okay? For example, if the mail is coming from Nigeria, maybe that's a signal. Okay? If the mail is asking for, it has the word password in it, that's a signal. Okay? So there's lots of signals. And each time you have a signal that increases the probability, that helps the spam detection. See how it works? So if you have many signals, like dozens, 20 signals, at the end of the day, the probability that you have spam with all the signals can be 0.999, and the spam filter will say, it's probably spam. But if it's not, if the probability that it's spam is 0.1, then it will say, no, it's not spam. Okay? So many signals say that it's somewhat likely, little bit likely to be spam, and it's almost truly spam, because the signals are independent. Okay? So you see how it works, You're combining all the signals, and for each signal, you calculate the posterior probability with Bayes' rule. So you see how it works, It's always the posterior, the probabilities change. So we're like in the landscape, probabilities, and new information comes in, B. B comes in, and this tells us something. Okay, this lets us compute the posterior. Okay, so it's B given that A is true, divided by the probability of B. Yeah? So it's the correction when B is coming in, A given B. Okay? So that's how you use Bayes' rule. You can compute, the probabilities will change as the information comes in. Okay? Right? So, are you understanding better Bayes' rule? Maybe you already understood all that. No? You can be honest. You already got it. If you already understood this before, then I say very good. That you are excellent. But even if you didn't, it's okay. Because Bayes' rule is kind of a confusing thing at first. It takes a while to understand what it's about. Okay? Okay, so that's introduction to Bayes' rule. We're going to use Bayes' rule now for the cascade. Okay? To see how the probabilities change as new information comes in. Because each time I look at a marble, new information is coming in. So we're going to use Bayes' rule to justify the reasoning. So the student will pick blue if the probability that it's majority blue is bigger than a half. Okay? So each student's decision, then, so the student decides majority blue or majority red. depends on the information the student has, so it's a conditional probability. It depends on what the student knows. Okay? So a priori, the priors here are all 0.5. So when we know nothing, the probability of majority blue and majority red are half. We don't know anything. But, I mean, there is something in the urn. It's either one or the other. But our ignorance is complete. That means we make no distinction between blue or red. But when we learn something, the probabilities will change. Okay, so let's say I can compute probability that majority blue is in the urn, given my information, student's information, we can maybe compute it and it's bigger than half. Then I can say it's going to be majority blue. I have more than 50% chance that it's majority blue and less that it's red, okay? And we have some information. So what we know from the situation is this. We know that majority blue and majority red are both half, 50%, if we know nothing yet. We know that there's 2/3 blues in the majority blues. So the probability that it's blue, given that it's majority blue, is 2/3, and the same for the red. This is saying that if we have 3 marbles, there's either 2 blue and 1 red, or 2 red and 1 blue. So the probability that it's blue or red, in either case, is 2/3. So this is what we know. And now, as the situation evolves, the student's information will evolve, and we can compute the probabilities. You see, we can make very precise what it means to be rational. Okay? Being rational means you say it's majority blue if it's bigger than half. Okay, so let's look at the first student. The first student. How should the first student guess? Okay, oops. How should the first student guess? So the first student, we need to compute this. Assume that the first student picks a marble and it's blue. Okay? What is the probability that it's majority blue given that I have picked a blue marble? So it's majority blue given blue. And the prior probability is majority blue. So we can compute all of this. Okay? So, what is it? So we have the probability is 0.5. And now we have the probability that it's blue given that it's majority blue. Well, that's 2/3, huh? And here we have the fun one. This one is a little bit harder. What's the probability that it's blue? We don't really know this because there's 2 possibilities. The probability that it's blue, because it's either majority blue or majority red in the urn. So it's probability majority red times the probability blue given majority red plus the probability that it's majority blue in the urn multiplied by the probability that it's blue given majority blue. Okay? So probability that it's blue, it depends on which situation we're in. We're either majority red or majority blue. In the majority red situation, it's this number. Majority blue, it's this. And we add them up because they're independent. It's one or the other. So majority red, the probability it's majority red is a half. Probability that's blue given majority red is 1/3. Probability that it's majority blue is a half. Probability that it's blue given that it's majority blue is 2/3. Okay, that's 1/2. So that's actually reasonable now. The probability that it's blue is 1/2 because it's a completely symmetric situation, huh? So probably the blue is 1/2, this one's 1/2. So if we compute this now, we get 1/2 times 2/3 over 1/2. So this moves up here, this becomes 2. It's 4/3 divided by 2, 2/3. Okay? So the probability that you have majority blue, given that I'm holding a blue in my hand, is 2/3. So the urn, it might still be majority red, huh? That's only 1/3 probability. And the other one is that it's blues, 2/3. Okay? So that's the first student. The first student should guess majority of whatever color that is picked in his hand. Because color is giving us a 2/3 probability of knowing what's in the urn. Okay? This is completely reasonable, right? It's very rational. Now, what about the second student? Well, the second student also picks a marble and looks at the color. But the second student also knows what the first student said. And we know the first student is going to say whatever that he sees in his hand. So the second student has 2 pieces of information, okay? Has what his own pick and his first student's pick, okay? So the second student has 2 pieces of information. So we have to compute what is probability of majority blue, given that we have 2 previous looking inside the urn, and they both give blue. So we have to compute this now. What is probability of majority blue given that we have 2 blues? Maybe it's going to be more than 2/3, huh? Okay. So on the slide I say leave the exercise to you. But maybe I do it, but after the break. Okay. So we have a break. So how would you do this? Maybe you can write down Bayes' formula and figure out how to compute all the pieces. Okay, so we'll have a break. Probability of the prior. So how should the second student guess? So what is the probability that there's a majority blue in the urn if I have 2 blues? If I get 2 blues, and you can compute that using Bayes again. So Bayes is very useful. Let me show you the formula. So the probability, we have majority blue, we write it like this, given we have blue, that's equal to the probability that it's majority blue. So this is the prior. This one is going to change. There's a correction factor. So the correction factor is the probability you have 2 blues, given that it's majority blue, divided by the probability that you have 2 blues. Okay. So this is how it works. So how do you compute this? Probability that it's majority blue, this is still 1/2. The probability that you have blue, if you have majority blue, so you pick 2 marbles and they're both blue, well, each time you pick one, it's 2/3, okay? And they're independent, so this is going to be 2/3 times 2/3 times 2/3. What is the probability that you have blue? No matter what. So if the urn has majority blue, you can do blue, but if the urn has majority red, you can do blue. So this gives you an overall probability of blue if you don't know what's majority. So this one you can compute, and you have to add up the 2 cases. Okay? So either it's majority blue or it's majority red. In each of these cases, you can get blue-blue, majority blue, or majority red. Okay? So you see, you split it up into two. So this is the overall probability of picking blue-blue if you don't know what the majorities are. So you have to take both of them into account. Okay? So each of these is a half. Since if you don't know anything, it's a half for each of them. And the probability that you have two blues, if you have majority blue, that's going to be the same as here. It's going to be 4/9. And the probability that you have two blues, if you have majority red, that's 1/3 times 1/3. It's 1/9. Okay? So this is 5/18. Funny number, huh? So this one is 5/18. This one is 4/9. So if you do the whole computation now, here is 1/2 times the correction factor, which is 4/9 over 5/18. That's 1/2 times 4/9 times 18 over 5. So 18 over 9, that's 2. 2 goes away. It's 4/5. It's interesting, huh? 80%. So if you take only one blue, then the first student will say it's 2/3 chance that it's majority blue if I take one blue. But if I take one blue and then again I take a blue, two blues, then the probability gets higher that it's majority blue, and it turns out to be 80%. Okay? So now the third student, this one I will leave for you. We assume the first two students have announced blue, and the third one draws a red marker. Okay? And the third student, what does the third student know? The third student knows that the first two students have genuine information. It's real, they really picked blue and blue. And the third student picks red. That means the third student has 3 pieces of information. Blue, blue, red. I pick the blue marble, I put it back. I pick the blue, put it back, and I pick a red. There's 3 pieces of information. So the third student has to compute this. What is the probability that it's majority blue if I pick blue, blue, and red? You can compute that using Bayes' rule. Okay? So good exercise. No, it's not blue, 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 but now blue, blue, red. So it's not as big a chance anymore that it's going to be blue as before. With blue, blue, it was 4/5. It was 80%. But blue, blue, red, it's going to be less. But if you do the computation using Bayes' rule, you get 2/3. And the third student is rational, okay? So this tells me I should ignore the red marble. Because from all my information, blue, blue, red, I know the probability that it's majority blue is 2/3. So all that I know tells me I should pick majority blue. Okay? So this is a cascade. Because actually this third student is ignoring this. But it's not the social pressure. It's rational computation of probability. So the cascade is something that comes rationally. It's not coming from social pressure. So the third student will guess blue and ignore their marble. And the fourth student the same. Because all the students beyond that only have 3 pieces of information. The information from student 1 and 2 and their own marble. The fourth student knows the first, the second, and the fourth. Because the third, we don't know what they picked. because they're always going to say blue, okay? So we don't know if they picked red or blue. So the cascade is formed, okay? Okay, now I want to do a formal model of this. So we did already some mathematics, so we compute using Bayesian. But now we want to do a formal model that's not connected to urns and marbles. We want to do a model where you have sequential decisions, okay? So you have a group of people, 1, 2, 3, who will sequentially make decisions. And the decision is very simple. They accept or reject something. This binary decision, okay? So there's some option. So you want to buy an iPhone, and either it's good or bad to buy an iPhone, okay? So, and the world is in 2 states. So this is the definition of the model. So the world is in 2 states, which we don't know which it is, but we know probabilities. It's either in state G, where the option is good idea, where iPhones are good, or it's in state B, where iPhones are bad idea, okay? So it's like a quantum superposition somehow. So we don't know which state the world is in. All we know is that it's probability P that the option is good idea, and probability 1 minus P, the option is bad idea, okay? That's the way it is, but we don't know. So the world is in this state, but we don't know. And individuals are not making decisions, okay? So they can either accept or reject the option. So accepting the option gives you a payoff, positive if it's a good idea, and negative if it's bad idea. So usually, if it's bad idea, you want to reject. Otherwise, you get negative payoff. So rejecting it gives 0. So the expected payoff, so now, assuming you have no extra information, you don't know anything, well, all you know is P and 1 minus P. That means your expected payoff is the sum of these 2. For the probability P, you get this number. Probability 1 minus P, you get this number. This one is negative, it's positive. So we're assuming expected is 0, that you're kind of in a balance. Okay? So that's the situation. And now you get signals. So this corresponds to picking the marble. You get a private signal. You get a little bit of secret information before you make your decision. So before you make your decision, you get this secret information, and it's either H or L. H says high, accepting is good. L, low, accepting is bad. So H is kind of saying you should accept, okay? And L says accepting, no, you shouldn't accept. But it's not certain information. So if the state is good, then H, you will get, so if the state is good, you will get H with probability greater than a half. Okay, so the H is a value, is valid thing. It gives you good information. But if it's good, then the L will be 1 minus that. Okay? Now, if the state of the world is bad, then you get the L with probability greater than a half. So the H and the L are giving you like hints, good hints. Okay? If the world is in good state, then you will get H with greater than half probability. If the world is in bad state, you would get L with greater than half probability. So the hint is valuable, but it's only giving you a little bit of information. Okay? The signal tends to point to the right decision. So H was saying, yeah, G is probably G. And L is saying, oh, it's probably B. Okay? And the probabilities are greater than a half. So you see, we're really in a world of probabilities here. We're computing with lots of partial information. Okay. Now, the individuals, they have to decide. on the information they have. So this is like with the urns. What do they know? They know their private signal, the H or the L, and they know what the previous people decided, the publicly decisions. That's what they know. And from this they have to decide. Okay? Now let's look at the first person. So there's nobody before. You only have the private signal. If you get an H or you get an L. What should you decide? Okay? So we have to make a computation here. So here, for example, the payoff, if you don't, before any decision, the payoff is Vg times P plus Vb 1 minus P is equal to 0. So before the signal, you have 0 payoff. But after the signal, these probabilities change. You see? This is the prior and posterior. So the signal will change the probability landscape. So if you get a signal H, then VPR of G becomes G given H. Because you've got an H, then your probability will turn into this. Okay? And the probability of B also is given H. So the Vg times that plus Vb times that changes because the two probabilities change. Okay? So the idea is that this one goes maybe higher, and this one goes maybe lower. And since Vg is positive and Vp is negative, the payoff is kind of becoming positive. Okay, right? Well, we can compute it. What is the new posterior probability of G? Okay, you can compute it. And I'm going to show it here, but you should do it as an exercise also. So this is Bayes' rule. So the prior is PR of G, posterior is G given H. And here's the correction factor. Okay. So H given G, and here you have the probability of H in the whole thing. So you have to look at both cases, when the world is G or B. So when the world is G, you have this probability. When the world is B, you have this. You have to sum both to get probability of H. And the probability of H given G, that's something that we know. Okay? H given G is more than a half. That means H is a good hint. It's a good hint. If you simplify this, you get this formula. P times Q divided by PQ plus 1 minus P times 1 minus Q. So P gives you the probability that the world is in good state, and Q is the quality of the hint. Okay? And if you do the same for B, you get this formula. So instead of payoff being 0, the new payoff is this. And it depends on P and Q. So Q is bigger than a half. You know that. Because H is a good hint. 1 minus Q is less than a half. This number is greater than 0. How do we know that? How can we figure that out? Well, because the Vg, so the denominator doesn't matter. We know it's positive. We just have to look at this numerator here. We have Vg times P, which is multiplied by Q, and Vb times 1 minus P, which is multiplied by 1 minus Q. But if Q is bigger than a half, then 1 minus Q is less than Q. That means this weight will be more than this one. And since this one is positive and this one is negative, the balance shifts. Instead of being 0, we get more weight to the positive and less weight to the negative, so it becomes positive. Okay? So you should convince yourself that this number is positive. It's greater than 0. So you have a payoff greater than 0, which means you do it. Okay, you accept the option. because your payoff is greater than 0. So if you get an H, you should accept. That means you assume the option is good. Okay? So this is what happens when you have one signal. What about when you have more than one signal? So remember, it's kind of a funny situation, huh? So you have individual 1, so person 1, he gets his private signal, H. Now we have person 2, who also has a private signal, which is going to be H or L, but also has public information. You have the decision. Decision is public. So person 2 knows this and the public decision. Okay? And person 3, person 3 here, has their private signal, H or L, but also knows all the public information. So here we have a public decision. And person 3 will know the previous public decisions and its private information. Okay? So each person knows its own little private signal, and it knows the public decisions of the ones before. And the public decision will be either accept or reject. Okay? So the first one has accepted because the signal was H. So here is the summary. This is, you can compute it, but let me first give you the summary. Assume you have now multiple people. Okay? You have multiple signals. Assume the individual gets a sequence of independent signals, okay? With high signals and low signals. Now we can already see, so this is one of the individuals that gets these signals. We can derive the following facts, okay? When there are more high signals than low signals, when A is greater than B, then the posterior probability will be higher. That G is good. That G is the case. When there are more low signals than high signals, then the posterior probability the world is good will be lower. So there's less chance that the world is good. And when we have the same number of signals, the probability doesn't change. Okay? So the idea is the individual should accept the option when A is greater than B, reject it when A is less than B, and doesn't matter when A is equal to B. Okay? So that's the kind of the decision of that. Let me okay. So this is the summary, because it's a more complicated computation. Okay? We can actually compute that. Let me just show you briefly. I'm not going to go in all of the detail of this. So this is computing using Bayes' rule. So here we have a sequence of signals. Okay? So what is the probability that the world is in a good state if you have this sequence S? So you have the prior probability times the correction. And if you compute this here, the probability of getting a given sequence, if the world is good, it's this. It's Q times A, those are high signals, 1 minus Q to the power B, which are bad signals. And you can multiply them because they're independent. And the probability of a particular sequence is you add both cases, when the world is good and when the world is in a bad state. You add both, and that gives you this more complicated expression, okay? You have P times this number, which is Q to the A, 1 minus Q to the B, plus 1 minus P times this number. And if you combine that, you get this formula. Now, we don't actually have to know the value of this complicated formula. We just have to compare it to P. Okay? When A is equal to B, this formula is equal to P. When A is equal to B, when A is equal to B, you can simplify, because you have P times this, plus 1 minus P times this, which are the same. That makes 1, so you have, and this is equal to 1. So when A is equal to B, this formula is equal to P. Let me show you what's happening here. Because it's a good kind of knowledge. You have to be able to do some kind of estimation. Okay? So let me pick the color. White. So if A is equal to B, then we have Q to the A, 1 minus Q to the A. In fact, that A is equal to B, divided by P times Q to the A, 1 minus Q to the A, plus 1 minus P, Q to the A, 1 minus Q to the A. If you combine these two, you get, this will turn into Q to the A, 1 minus Q to the A, because we have P times a number, plus 1 minus P times the same number. So we have this. And then we can divide it out here, okay? And we have only the p's left. So when A is equal to B, this number is equal to P. Well, what happens when A is greater than B? What happens to this number? Does it get bigger or smaller? See, that's the question, huh? Does this posterior probability get bigger or smaller? Well, we do know something about Q. We know that Q is bigger than a half. So Q is bigger than 1 minus Q. That means when A is greater than B, these two sides will change in different ways. This one, the 1 minus Q to the A, here we have Q to the A. But Q is bigger than 1 minus Q. Okay? And 1 minus Q to the B, so B is smaller than A. So basically, what's going to happen is that the weight is going to, what's going to happen there? So we have to compare it to P. So what happens? We have this number is divided into two numbers. Okay. So I'm not sure what's going to happen there. Maybe I explain it as P. So let me explain this one next time, okay? But I can leave it as exercise, but and I will explain it next time. So the question is, this, when A is equal to B, this is equal to P, okay? But what happens when A is greater than B? Does this number get bigger or smaller than P, okay? And we know that Q is bigger than a half. So that will tell us what happens to the conditional probability. If there's more than A's, will it be more likely that there will be true, that the world is good or not? Okay. So normally we will get this situation. We'll get that the probability will increase. Okay. So I will finish this computation next time. Okay. Now let's take a step back and see how you get cascades in general. Okay? So I don't want to do more complicated computations now. We've made all the computations we need to do. Now I want to see, when do cascades happen? Okay? So assume that individuals make decisions in sequence. Each individual sees the earlier people's action, but not their private information. So each individual knows their own private signal, but it will plus the accept, reject decisions of the earlier ones. Okay? So they don't see the private signals of the earlier ones. Okay. Now, what's going to happen? Sometimes you will have a cascade, and sometimes you will not. So let me show what happens. So person one will follow his private signal. Person two knows that person one's decision reveals the private signal. That means person two actually gets two signals. Okay? If they are the same, that's the thing to do. If it's both H or something, then you do G. If they are different, then you follow the private signals. You have a tiebreak. So person two also always follows their own signal. This is similar to what we saw before, but now it's more general. So person three knows that 1 and 2 both revealed their signals, and person 3 has their own signal. So person 3 has 3 independent signals, okay? And person 3 will follow the majority, okay? If person 1 and 2 make opposite decisions, person 3 will use their own signal, okay? And future people know that this is useful, because the first 2 people made different decisions, so you know the third one is useful. But if person 1 and 2 made the same decision, then person 3 will follow this. So future people will know that person 3 is now a zombie and is following the cascade. Okay? So there's 2 possibilities here. If person 1 and 2 are opposite, then person 3 has their own decision, using their own signal. But if person 1 and 2 made the same decision, then person 3 will follow the cascade. Okay? Now what about future people beyond person 3? Okay, person n greater than 3. Suppose all earlier people followed their signals. So that's possible, huh? So as long as you're not in a cascade, so you can keep going and not in a cascade, then then you know that the decisions are the same as the private information. As long as you're not in a cascade, you're getting lots of useful information. Okay? So suppose all earlier people followed their signals. That means we're not in a cascade. Person n knows it. If the number of accepts equal the number of rejects, then the n is a tiebreaker, follows their own signal. If the number of accepts differs from 1, okay, then there's 2 possibilities. Either n signal is the same as the lower, or n signal is the same as the higher. It either makes them indifferent, so the 2 numbers are the same again, or it makes the difference a difference by 2. It reinforces the majority. So n follows their own signal. And the final one, if the number of accepts differs by 2 or more, then nothing that n can do changes anything, and we're in a cascade. So you see, the tipping point is this one here. If the number of accepts differs from 1, then there's 2 possibilities. Either you go into a cascade, or you go back to being indifferent. Okay? So you can make a kind of graph of what's going on here. So these are the people, 1, 2, 3, and the decisions. And here on the y-axis is the accepts minus the rejects. So person 1 accepts, so we're here. Person 2 rejects, so we're here. They get a private signal and they reject because of that. So we're back to 0. Person 3 rejects because of the signal. So we're at -1. Person 4 accepts, so we're again at 0. Person 5 rejects. Person 6 accepts. Person 7 accepts. But now we have something special. Person 8 picks the signal so that it also accepts. So now we're done. Now we're in a cascade. So you see it's kind of going to bounce up and down. As soon as it gets to 2, as soon as the difference gets to 2 here, then person 9 cannot change anything. Because person 9 cannot make it go back down to 0. It's still going to be majority. So once the difference becomes 2, then it's a cascade. Okay? So a cascade begins when the number of accepts and rejects, the difference between the number of accepts and rejects reaches 2. As long as it's less than 2, it's not cascading, it's kind of a delayed thing. Everyone does their own signal. So as long as the number of accepts and rejects differs by at most 1, the people are still going to follow their private signal. They're either going to reinforce the majority or they go back to equality. So it's very improbable that this is going to stay forever in this narrow band. Eventually, there's going to be 2 accepts in a row, or 2 rejects in a row, and then it's cascade. So you cannot avoid the cascade forever. So you're kind of avoiding it here, but it's all probabilistic. It all depends on the private signal. And eventually, it's almost sure that you're going to get 2 accepts or 2 rejects. So as the number of people increases without bounds, the probability of a cascade will converge to 1. So it's basically with probability 1, the cascade is going to be formed. Okay? See, it's a little bit complicated. You can delay cascades. It can be delayed. I had a diagram before, but the urns, you can delay it. But eventually, it will tip over in one direction, and the cascade will be formed. So cascades are almost always going to be formed. Okay? Eventually. So this is the final conclusion, actually, from the formal model. Okay? Now let's take a step back. No more mathematics. Is to think a little what happens in the real world. Okay? This is idealized model. If it's in more realistic cases, well, people might only see some of the early decisions. Or the people might not get exactly the same kinds of private signals, or the payoffs might be different. Okay? So it might not be exactly like this. But the conclusions will still be similar. Okay? When people see each other's public decisions, but not their private knowledge, then the system can lock in to one or the other, can tip over to a cascade. See, if you see the private knowledge, then you have lots of information and you can make a good decision. But if you see only the public decision, then you don't see the private. Once the system locks in to one state, it will always be the same public decision, even if the private knowledge changes. Okay? So this is what enables cascade, is when you see what people do in public, but you don't know what they know in private. And this is very common, of course. In the real world, it's hard to read people's minds. So this happens a lot. So this is what enables cascades in general. Okay? That you see the public information decisions, but not the private knowledge. Okay, some lessons from this. So the observations from Erding are reinforced. So the cascade can be wrong, of course. If accepting is a bad idea, well, the probability of accepting is still bigger than 0. So the 2 people get high signals by bad chance, then you can immediately have a cascade, even though it's wrong. So the cascade can be wrong. It can also be based on very little information. Once you have a cascade, then you don't see the private information anymore. So if the cascade starts quickly, most of the private information is ignored. So if the cascade takes a long time, you will see a lot of private information until the cascade forms. Then it's done. Okay. After the cascade forms, you don't see private information. And also, final one, cascade is fragile. If you have more information than most people, let's say you get extra private signals, maybe you get 2 private signals instead of 1, then you can break the cascade. Okay? Or if you make your private signals public, if you make them public, you can overturn the cascade. So the main conclusion is, be careful in drawing conclusions from the behavior of a crowd. A crowd can be wrong, even if everybody is rational. Second lesson, you can be part of a cascade, and if you notice that you're part of a cascade, then you can immediately realize that your rational thinking is wrong because you're going into a cascade, and you can break it. Okay? So in general, the idea is that cascades are bad things, and you don't want them to happen. Okay, let me tell 2 more little stories. First little story, there's a book called Wisdom of Crowds by James Surowiecki, and it says that a lot of people together can be very smart. For example, how many jelly beans are there in a jar? If you take a lot of guesses and you take the average or the median, then you get a very good estimate. Okay? Even though people are mostly ignorant. So why is that when we are saying today that the crowds are going to be cascading and they're very stupid? Well, the difference is, for Surowiecki, the people are independently guessing. Whereas for cascades, the people are making decisions sequentially. So this is a big difference. Independence is much smarter than sequential decisions. Okay? So there's no conflict. So the trick is independent decisions versus sequential decisions. And I want to make a final point, because this is a very Belgian situation. You've heard of this approach called tour de table? You ever been in a meeting where people do tour de table? It's very Belgian, huh? So you're in a meeting, everyone's sitting around, and they want everyone's opinion. So in Belgium, the usual way is to do a tour de table. You ask each person to give their opinion, talk like that, around the table, in sequence. This is exactly the situation that gives you a cascade, okay? If a few people initially favor one option, and they give some reasons for it, but they have some private reasons that you don't know, the other people might be concluding, oh, maybe, yeah, they're right, I should say that, I should agree with that. And even if they didn't like option A, they may tend to agree with A. And it's not even social pressure. It might be actually rational, because people later on in the circle will be thinking, I have information from these people, the extra information points to A. But that can be wrong. Okay? So tour de table is actually not a good idea. If you're in a meeting, you can cite me on that. So much better is this way, this two-phase approach. Everybody writes down their opinion on a piece of paper in secret, independently, and then in the second phase, you make all the opinions public. So there's no sequentiality, it's independent decisions. This is much better for making good decisions, okay? So if you're in a meeting, you can remember that. So that's a lesson for Belgians. Been in tour de table? You ever seen that? I've been in that very, very much, okay, in meetings. It's a very Belgian thing, okay? So let me summarize. So the whole point of today's lecture is sequential decision information. where people have private information and they see the public decisions from the other people. Okay? And we made a formal model, as usual, using Bayes' rule. So I actually explained also Bayes' rule. Even if people are rational, this can go wrong. You can have information cascades where the system gets locked in with a small amount of information. So it's much better to do independent decision making, okay? And not sequential decision making. And in realistic situations, it happens a lot, even if the model, it's not exactly like the formal model. However, the good news is that it's fragile, and you can usually break the cascade if you introduce new information. Okay? So that's the lesson for today. Okay, so there you go, and the final lesson for Belgians is don't do two of the tablet. So that's all for today. Thank you.